go ahead and start. Okay. On Monday, we were talking about configuration of electrons, and there were a number of parts to that. There's the shell, the subshell, the orbitals, and then the electrons and electron spin within those orbitals. Okay, so let's do a neutral one just to kind of get us started here. And let's do, let's say, oh, I don't know, let's do sodium. Let's do a real simple one. Okay, so we're going to do neutral sodium. Okay, that's sodium metal. And if we go up here, there's sodium. So as you know, all electronic configurations contain both core electrons and valence electrons. And those core electrons are represented usually by the closest noble gas, which is up one and all the way to the right. So that means that's going to be fluorine. So to represent sodium, the abbreviated way, the shortened way, we would go and then 3s1. Okay. The other way would be the longhand way, which we would represent by so the 3s1 electron is the valence electron. Again, the valence electrons are the outermost electrons. They contribute 99.9999% of the chemistry of an element. And that's why those are, the reason why we focus on valence electrons is for that reason. Okay. Let me do one more. That's a bit more complicated. Let's do cobalt. Neutral cobalt. Okay. And notice cobalt is written with the symbol for cobalt is written with 2 letters. Always the first letter of a symbol is always uppercase. The second one is, if there is a second one, is always lowercase. No exceptions. Because if we were to write cobalt like that, that would indicate carbon monoxide, which is not the same as cobalt. Big C, little o, big C, big O. So it's crucial that you follow that protocol. And whenever there are 2 letters to the symbol of an element, the second one is always lowercase. Okay, so cobalt. If we look at the abbreviated version, it's going to be up 1 row and over, that's argon. And you're looking at 4s2 as you go across here. We are 1, 2, 3, 4, 5, 6, 7 into the D's. And remember, the D's are down 1, so that means 3d7. So that was the neutral cobalt. Now, I mentioned, are there any questions so far in doing the neutral ones? Hopefully you've all practiced this, like I mentioned on Monday before today, because we're getting into ions now, and ions also have an electronic configuration. And to understand the ions, you've got to be able to first do that neutral version of the element. Okay. So let's review what an ion is. Okay. Let's just. Okay. When the number of electrons do not equal the number of protons. Okay. In which case, since electrons are negatively charged, protons are positively charged, that means we're going to have a net charge whenever we have an imbalance of electrons and protons.
So I'm sorry, that should say does not equal protons?
Correct. Correct. When the electrons and protons are equal, that's a neutral compound or neutral element. Okay.
Yes, thank you.
So you're saying that should be a not there? Is that where you're going with that?
That was, yes, exactly. Thank you.
Okay. Gotta keep me honest, you guys. All right. Yes, and because they're not equal, then there's a net charge, either positive or negative. Positive ions are called cations, negative ones are called anions. Now, the important thing about an ion, they do not exist by themselves. An ion has to have two parts. It has to have a cation part and an anion part. So an ion doesn't exist by itself in nature. It has to have something accompanying it, because there's no charge, isolated charge in nature. There's always some balance there. Okay. For example, table salt. We have sodium chloride. Sodium is the cation, always listed first. Anion, the chloride, is listed second. Now, in an ion pair, the electrons are transferred from the, let's frame this. Okay, and during that process, the electrons are transferred from the cation to the anion. So the cation loses electrons, anion gains electrons. Whenever you donate an electron, you have to have a recipient. If you donate 3 electrons, the recipient receives 3 electrons. If you donate 3 electrons, it becomes a positive 3. If you receive 3 electrons, it becomes a negative 3. And that's now we're going to get into this a lot, this whole ion balancing in another unit. But the main thing is there's always an ion that exists of the opposite charge. In other words, if there's a cation, there's an anion there, and this is in nature now. Now, the reason why these ions form is based on the stuff we've been saying in this course up to this date. Why do you think ions form?
it's more stable than what existed before it?
Exactly. Exactly. You know, the trend in this class is stability, stability, stability. So if things can change and make things more stable, frequently it does. Okay, so then why is sodium forms an ion like that, and as opposed to staying a neutral metal? Okay, so let's look at the electronic configuration of that sodium ion. Now remember, this is what okay, so that's neutral sodium. Now sodium plus is going to lose an electron. Well, we have a bunch of electrons there to lose. Now, so of all the electrons there are 11 electrons. Which ones do you think would be candidates to leave? Form the +1 cation.
The valence electron,
Yes, and why?
because they don't fill the orbit.
Yes, that's true. If you were going to pluck an electron out of a batch of electrons, would you pluck the most stable electron or the least stable electron?
Least stable?
Yeah. The stable ones are stable. Why would they want to leave? So you want to, the one that with the least stability is going to leave. Now, there's a couple of reasons why that guy is the least stable. One, it's shell. Let's just write those down, okay? The shell is higher than the core electrons. It is in a half full subshell as opposed to full shells. Now, what do I mean by that? There are definite stability differences between how the electron configuration is set up. The most stable configuration for that is when we have the shell is totally full. Totally full. Okay. When I say a shell, it's shell 1, 2, 3, 4, all the way up to 7. If all those are full, then those are very stable. If they're not full, then they're less stable. Okay. The next one down is we're looking at a subshell. If a subshell is full, that's stable. Not as stable as a shell, but definitely stable. And then half full. Now remember on Monday I mentioned that nature likes geometric symmetry. And as the full shell is got the electrons placed around it in the most symmetrical way. So everything in terms of electrons, remember electrons are negatively charged, they're going to be repelling one another. So if it's symmetrically set up, then the repulsion is basically kind of balanced. So again, nature likes symmetry because it's more stable. Okay, now we're going to see that theme throughout this class on symmetry. Frequently, molecules will form. One will form more in a reaction form more because it's more symmetrical than another one. Lots of reasons. Okay, it has to do with electrons are repulsing one another. Okay, So these are the three categories in terms of looking at the way an electron is filling or leaving a configuration. Okay, so these guys have full shells, so they're super stable. These two electrons here. These 8 electrons here make up shell number 2, also full. So very stable. And that's one of the reasons why core electrons are so stable. It's because their shells are full. Now, this 1 electron in the 3s shell, subshell, is half full because it has 1 instead of 2. So it's not as stable as the core electrons, which have a full shell. So what's sitting down here? So that is why that is the candidate electron to leave. It's because its shell is higher. When I say higher, it's further from the nucleus. As the shell number gets larger, those orbitals are farther and farther away from the nucleus, so there's less and less attraction. Okay, so the shell's higher, and it's not a full subshell, it's a half full subshell. Okay, so that's one reason that's a candidate to leave. Now, look what happens when that electron leaves. What has happened when we went from here to there? We went from half subshell to a full subshell. Okay, so this is basically made up of just core electrons, super stable. So the driving force for the sodium +1 ion forming is that we go from a partially filled subshell to a full-blown shell, full shell. And that mimics the noble gas configuration. So basically, sodium is losing an electron to be like the noble gas configuration. Oh, neon. So if an ion can form to be like a noble gas, it'll do it. For excuse me, for stability reasons. Okay, so the driving force for forming an ion, stability. Driving force, if it can happen and form a full shell by electrons leaving, it'll happen. Okay, does that make sense? This is why I wanted you to practice the neutral electron configurations before today, because you have to start with the neutral. And then if the ion is a -1, +1, -2, +2, or whatever, you're going to be adding and subtracting electrons. The question is if you're taking electrons away, which ones do you take away? Okay, so let's look now at fluorine. Okay, so fluorine is 1s2, 2s2, 2p5. Now let's look at the orbital version of this. Okay, we're not going to look at, I'm just going to look at the valence here. Okay, so we've got the S, P. The S's are full, and the P's are partially full. Okay, so the problem with, and this would be, the problem with fluorine is it's not particularly in this list up here. It's not full shell, it's not a full subshell, it's not a half full subshell. It's kind of blah. And again, it's not particularly symmetrical because of how nature is. Okay, so one way fluorine can become stable is it can gain an electron. So if we look at if we can gain an electron here, that becomes a full shell. As soon as you gain that electron, it becomes a full shell, super stable. So this would be a -1 cation. Next would be a -1 anion. So what it's doing, it's gaining an electron to become more stable, and it becomes really stable because the whole shell is full now. So it's gaining an electron for the same reason sodium is losing an electron, to become a full shell, to mimic the electronic configuration of the noble gases. Noble gases are all full shell, core electrons only. Okay, so fluorine is the opposite of sodium. Sodium loses an electron to become full shell. Fluorine gains an electron to be full shell. Now, if we look at, does that make sense so far?
Yes.
Remember, I always said that there's a cation and an anion pair. So sodium wants to lose an electron, fluorine wants to gain one. So the electron from sodium goes over to fluorine, and that becomes, so they both win. Now, the reason why sodium is so prevalent in the world is because the sodium cation is so stable, extremely stable. Sodium is all over the place. Okay, now that was a that was a couple examples. Let's do some more examples now. Let's look at our, let's see here. Let's look at our cobalt now. Now we're looking at the valence electrons for cobalt. Okay, it's going to be two 4s's. 1, 2, 3, 4, 5, 6, 7 3Ds. Just like here. Let's look at the orbitals. 2 S's, 7 Ds. Now, cobalt forms cations. It loses electrons. So what can we do to cobalt to make it more stable?
We can pair it with something that will give it 3 electrons.
Yes, that's one way. No, I'm serious, that's one way. Normally, the metals form cations, just in general. The non-metals form anions in general. So you're absolutely right what you just said, because by adding 3 electrons, that would give us a full subshell, a D subshell.
But since it's a non-metal, it's more likely to, it's going to lose.
Yeah, but it's a metal too.
Oh, it is. Got it.
Yeah, non-metals are top right on the periodic table. Then we have the metalloids, and then everything else is metals. Okay, so we have. What do you want to do then? What's the first thing we can do that would make sense on this configuration? Now you just mentioned adding 3 electrons, and that would be perfect, except it's metal. But your logic is perfect. So let's reverse the logic. Instead of adding electrons, we're going to do the opposite. Which ones are we going to take away so that cobalt becomes a cation? Which are some candidates?
Well, the 4s2 is stable, so we would leave that alone. So somewhere in the last 3, since those areas are not full.
We want to now remember. Keep these in mind. In other words, full shell, full subshell, half full subshell are the most stable. Now, cobalt, neutral cobalt is none of those. So you mentioned one thing, by adding 3 electrons would give us a full subshell.
Yes, correct.
So continue that thought now with removing electrons.
Okay, so if we removed the 3 electrons.
Okay. So it'd be like this. Like that?
Yes. Does that work?
No. The reason why it wouldn't work is because, one, we have, remember Hudd's principle, we have to fill all the orbitals first with 1 electron, and then we start spinning it up. Okay.
Got it.
So this is less stable by doing it that way, instead of filling them up one by one. So let's add these back. So instead of it taking away those 3, what could you take away instead?
I think I'm thinking about this too hard.
Well, remember the three levels of stability: full shell, full subshell, half full subshell. Well,
So we could take the 2 electrons away, and we'd have a partially full.
yeah, exactly. So if we take these 2 away, we have a what?
It's half full now, which is better than before.
Yeah, exactly.
Or more stable, I should say.
Yeah, exactly. Exactly. So that means cobalt in this case would be cobalt plus 2. So that configuration would be a 4s2, 3d5.
Okay, thank you. This is clicking for me now.
Good. Okay. Now there's another way we could do this. Is remember I mentioned before that the higher the shell number, the further they are away from the nucleus. So these two electrons would also be candidates. So if we remove those, because they're far away from the nucleus, shell 4 versus shell 3, it would look like this. So that would also be a candidate. And you'll find that most of the transition metals will usually lose 2 electrons. And they're always the s electrons they lose, plus other things. Now in this case, we have cobalt plus 2, cobalt plus 4. And those are 2 common ions that cobalt will form. And this is the reason why. So we would write this. And the reason why I put the 0 in, just to indicate that that is an empty orbital or empty subshell that normally gets full. You can also write 4p0, but that's to the right. That there's not enough electrons to go over there. But if there's enough electrons to fill it, like on the S, I like to put the 0 in there just for clarity. Okay, so basically, we are looking to do this. I'm going to add or subtract electrons to achieve this. And that's the reason the ions are forming. Okay, let's look at zinc. Now zinc is going to be that's shell 4. So zinc is going to be zinc is in pretty good shape. It's got a full S subshell, full D subshell. So if it was going to form an ion, what would it be?
Zinc is technically in the metal family, yes?
Yeah, so it's going to lose electrons.
Got it.
Well, I mean, right now we have those 2 subshells full. Now we don't have the P's full, so the shell itself is not full. We got 2 full subshells. Now, you can make a case, well, why would zinc want to do anything? It's in pretty good shape right now. Well, you do find zinc metal in nature, but you frequently find it also as an ion. So how could we justify a zinc ion forming?
matches with something that gives it enough electrons to complete the shell?
That would mean it's going to be an anion. Remember, metal.
Oh, and we're losing.
Yeah, metals lose electrons. But your thinking is right on. Thinking is right on. Well, between these electrons and the D and the S's, which are less stable?
The S's?
Yes, correct. Why?
Because they're farther away and less stable
Yeah.
from the nucleus.
Yeah, they're further away because the 4 versus the 3. So those are candidates to go if we're going to lose electrons as opposed to the Ds. Because with the Ds, if we just took one, it would go from a full subshell to nothing. So we'd have to take 5 of them to go from a full subshell to a half subshell, and that's a lot of electrons to go. Where the S's, we can either take 1 or 2. Now, if we took 1, it would look like this. If we took 2, it would look like, oops, it would look like that. So between the two, this would be zinc plus 1, zinc plus 2. Between the two, the zinc plus 1 plus 2, which do you think is more stable? Now we're leaving the Ds because there are too many electrons to go, to leave. So
This is zinc plus 2,
yes, that's correct. Why?
because zinc plus 1 just has that 1 electron there, but zinc plus 2 is just empty.
Yeah, you can make a case saying that by, well, this is half full here, right? And this is got nothing here. But with it nothing there, that means it doesn't count at all. And we're just looking at a full full subshell here. This is half in a full. And again, the S's are further away, and they typically leave together. So you're going to find both of these ions in nature, and you'll find more +2s and +1s because this combination, the +2 combination, is more stable. Now, there's some exceptions to all these nice rules. There are not very many of them, but there are some exceptions. And the main thing I want you to get out of this here is why a normal ion will form. The reason why a normal ion will form is to go here, to form either a full shell, a full subshell, or a half full subshell. That's the driving force. And again, it's a stability driving force. Now, I've given you some extra worksheets, as you know, and one of them is on ions. It gives you lots of practice there. Now, Jacob, are you on?
Yes.
Would you mind if anyone joined our 9:30 or our Friday session?
No, not at all.
Okay, Jacob arranged for me to have a Zoom session Friday at 6:30. If any of you are interested in joining that, I can, in fact, I think I'll just send out an invitation to the whole class. I'd be glad to, go over anything you'd like for Unit 2. So it's kind of a nice review session. Okay, so what I want you to do is, are there any questions about this ion formation? It's based solely on being able to do the electronic configuration. You've got to be able to do that before you can make any sense out of why an ion will form. Okay.
Oh, there was a question in the chat. Somebody asked if you could do one for copper.
Remember I talked about exceptions? Copper family is an exception. The chromium family is an exception. Okay, if we look at copper, copper is going to be right here next to zinc. So it's going to have three it's going to have 9 3D electrons. Okay, and I want you to look at that. So let's look at copper now. And that goes for everything in the copper family, because the valence in the copper family, they're all the same valence, electronic configuration valence. Okay, so this is what copper looks like. It's going to have a 4s2 3d9. Okay. What copper does, copper is kind of looking at, okay, I'm not particularly stable. Is there a way I can kind of rearrange my electrons slightly differently so that I can have these guys up here fulfilled better? Okay. What copper does, it's kind of tricky. What copper does is it takes one of these s electrons and moves it over here. So you're saying, what? This is a full subshell. So we've taken a full and made it a half. We've destabilized the S's. Destabilized. Ferguson, you told me that the reason things form is to become more stable, not less stable. But what have we done here? This is now a full subshell. We've gone from kind of a nothing up here to a full subshell. Also, that subshell, that D subshell has 10 electrons in it. That S that we destabilized had 2. So what we've done is we've destabilized the S subshell and we stabilized a much larger subshell. So that's what copper does. So copper configuration is not that. It is 4s1 3d10. And also silver and gold are the same way. So internally, copper is going, a bigger full subshell is better than a small destabilized subshell. Reminds me of the movie, Star Trek movie, where Spock gets irradiated and he's behind a wall and he's talking to Kirk and he says, the needs of the few do not outweigh the needs of the many. Remember that? It was an early one. behind a super thick, looks like a plexiglass wall. And so here we are. We're stabilizing the many, destabilizing the few. And that's what's going on inside of copper. Does that make sense?
Yes.
Okay, I'm going to do chromium while we're at it. Chromium is kind of same thing. If you look at chromium, it's 4s2, 3d4. So what happens with chromium, it's sort of the same as copper, where we've taken an S and moved it over to a D. So we've gone, so this is now a half subshell, from nothing to a half subshell. And this is full to a half subshell. So we've destabilized the S, stabilized the D. For the same reasons that copper did it. So the whole chromium family, because the valence configuration for the chromium family is the same, they all do it. So exactly the same reason, copper and chromium. Now those are two exceptions that are very widely talked about, the chromium and the copper families. And there's some other weird ones. The bigger the atoms become, there's a lot of weird stuff that goes on that I'm not going to talk about. But basically, all that shifting of electrons is for the same reason, stability. And what they do is the atom is playing these little games, shift one electron here, or we're going to destabilize this, we're going to stabilize that. And the stabilization is more than destabilization. So it nets out to be better. Okay, so that's as complicated as this class is going to get, those two examples. And we're talking about, by the way, copper metal, chromium metal. Now, copper can form ions. For example, if we look at this configuration here, if it loses one electron here, forms copper +1, or it could lose these two and form copper +2. Copper +1 is very, very common because when it's in this configuration down here, by losing that one 4s electron, you maintain the full subshell. So the copper +1 are very common, more common than the +2 for that reason. Okay, the last thing I want to cover in this unit are the three trends. We talked about two of them. First one is size. We have as we go from top right to bottom left, things get bigger. Many reasons it gets bigger. One reason is it just has more stuff in it. Cesium has 265 protons and neutrons and a whole bunch of electrons. So it's just got more stuff in it. Got more stuff in it. the more electronegativity we have, which is the other term we talked about before, the more the element becomes smaller because it's seeking out electrons, so it's becoming smaller. One of the reasons it's seeking out electrons is the example we gave earlier. Fluoride wants to form a -1 anion dearly because it's so incredibly stable. So it wants to gain an electron at all costs. These guys want to lose electrons for the same reason fluorine wants to gain one. So that's why its electronegativity is low. Fluorine is high. One we haven't talked about is ionization energy. Okay. Ionization energy is the energy to pull off, the first ionization energy, I should say, is the energy it takes to pull off the outermost electron. Well, the electrons with the most electronegativity are going to be hardest to pull off. So that means that fluorine does not want to lose an electron. It wants to gain an electron. So it's the energy to pull off that one electron from fluorine is going to be the toughest because it wants to hold on to its electrons the most. Bottom left, they want to get rid of their electrons to become more stable. So its ionization energy required to pull off that outermost electron is the least. So electronegativity and ionization energy go hand in hand for the same reason. So those are the three trends on the periodic table. Okay, so that concludes Unit 2. We talked about the groups and early on in Unit 2 here. These are the ones I want you to know: the alkali metals, the alkali earth metals, halogens, noble gases. Remember the metalloids are here. These are non-metals. They usually form anions. Metals, and they usually form cations. Frequently, whenever we have an ionic compound forming, we have a metal plus a non-metal. Because cations are positive, anions are negative. Like sodium chloride. Okay. So what I want you to do between now and Friday, if you haven't taken your test yet. Now on Friday, I'm not going to be answering test questions, obviously, because you're going to be in the middle. And once you start the test, you have to finish it. But anyone is welcome to come on Friday at 6:30. I'll send out a Zoom session. In fact, Jacob, would you mind? Are you still on?
Yes.
Would you mind sending that Zoom session info out to the class?
Okay.
I appreciate it. Thank you. Okay. All right. Are there any questions about anything, you guys?
Oh, just for further clarification, we can have our periodic table and any of our lecture notes for the exam, correct?
Correct.
Okay, thank you.
And most importantly, have your notes not under Windows tab. Because all your tabs will go away except for your tests tab.
Yes, I made that mistake on the quiz, but luckily it was only 8-point quiz.
And now that's it. Those are 8 raw points. I convert all those to 20 points. Same with the tests. The tests are worth 100 points, and I convert the raw points to 100 points.
Okay, thank you.
So you can either have them on a tablet, for example, like Jacob was talking about having a tablet with the PDFs on it and maybe some paper notes combination. Any of that works. Okay, let's see. I'm going to stop recording here.